you ready.
Okay, yeah, so my name is Eoghan, and today I'm just presenting you my FYP. It's called Machine Learning Applied to Wireless EEG Signals. Sorry. So for this project, what I did was I captured EEG signals from thought and used that to control a box inside a GUI. So on the right hand side here, I have Julie there, and she's controlling the box inside that GUI application using her thoughts. So she's thinking left and right and controlling the box with those thoughts. These EEG signals are captured using the headset there. It's called a brain-computer interface, and once the signals are captured, they're applied to a neural network, and the neural network is trained, and then the neural network can classify a live stream of data sets. So yeah, so what is a brain-computer interface? So as I shown there, that's the brain-computer interface, and it has sensors on top of the headset that capture the signal when from the brain, and these are then sent to a microcontroller that's also located on the headset, where data is processed, and then it sends the information then to the computer, where it's used to train the neural network. Generally, these are used to diagnose brain disorders and restore brain or functions for people with neuromuscular disorders. So how does hardware work? So first of all, when the EEG signal is captured, it's a very low voltage, so we have to amplify that. So after we amplify it, we then filter it to avoid aliasing, noise in the signal. It's then just converted to a digital output, and when we have it in numbers, basically, we send it via Bluetooth to the computer. For this project, though, I use an EMG signal. So that's when you contract your hand. When you contract your hand, you release an electrical signal, and that's what an EMG signal is. Generally, an EMG signal has been 0 and 10 millivolts. So that's far larger voltage than an EEG signal, which is between 10 and 100 microvolts. So it made it very easy to train the neural network using that. And we can see this here. So when the user blinked with the right eye, you can definitely see it here in channel 2 when it's captured. However, when the user thinks right, it's very hard to see where it's captured. And although there is some voltage here in channel 5, most of that is noise. So you can see the EMG signal is far better to train, at least to train the neural network initially, before applying it to an EEG signal. So after we have the signal captured, it's then processed on the computer. So how is this done? So I experimented with both the frequency domain and the time domain, and I found that basically the frequency domain gives a better accuracy. So I use a fast Fourier transform to convert the data set into the frequency domain, and I then restrict it to 1 to 49 Hertz. This is to make sure there's no interference from other devices while I'm using the headset. Yeah, so then after identifying that I was using the frequency domain and EMG data set, I trained 2 different machine learning algorithms to see which one would be better. And we found out basically that the CNN, which is convolutional neural network, was better than an SVN, which is a support vector machine. As we can see here, the CNN got up to an accuracy of 66% with an inference time of 43.8 seconds. Now, an inference time means the incoming data set, how long it took the neural network to classify each sample. And in total, there was 800 samples during each of the training sessions. I can get it up. I got up the accuracy up to 76%, but that came with overfitting. Overfitting means that the neural network starts to fit itself more to the train set, and when you introduce a new data set, it doesn't classify as good as it does the training set. When we compare that then to an SVM, the accuracy is not as good, and it overfits a lot more, but it is quicker in terms of inference time. You could argue that I didn't train the SVM as much. I only used a data set of 6,000 samples, whereas I used 180,000 for the CNN. But that's because the SVN has an impractical build time. It takes basically it takes forever to make one SVM if the data set is too large. So that's why we went with a CNN. So then after getting the CNN working, I applied it then to an EEG signal. So that's the signal produced from thought. Well, we got an accuracy of 66%. It did overfit to the training set, and the same furnace time. So when I mean it's overfitting with 13%, in reality, what was happening was during the training session, the user could control the GUI, and if they started testing straight after the training set and didn't move the headset, but once they took the headset off and tried to put it back on, you couldn't control it, because the EEG signal is so subtle and so small, as we talked about, that noise basically interferes with the process. So here I have two videos, one of myself controlling the GUI with EMG from eye blinking. So I blink with the left eye and the right eye. And here you can see the inference time, because you saw when I was blinking. So the thing will go a little bit to the right, so that's just an inaccuracy. But then it'll go to the left. So it'll go to the left there now in a second. Yeah, starting to go to the left, and then it will eventually start going back to the right. And that's you controlled using eye blinking. Now over here on this side, it's harder to tell that there is latency or delay, but there was, Judy was thinking about 9 or 10 seconds prior to the thing moving, and she was thinking right, left, right. And that's how she's controlling the GUI. So she was just thinking the word. Yeah, and that had a bit of overfitting. So as I was saying, she couldn't replicate it after the training session. So to conclude, the CNN outperformed the SVM just because it was just easier to do and it was more accurate at the end of the day. To really develop a neural network for EEG signals, you need a large data set and use different participants and a lot of training. I'd say over 1 million data sets anyway to get anywhere decent. Large processing power to reduce the latency or the inference time, as I was talking about. That would really help with to help the GUI work in real time. And adjustable headsets. So maybe a headset with Velcro would help you get a more accurate signal every time, rather than with that headset it was hard plastic and it was just very hard to put in the same place once you where you originally had it. Thanks for listening there, and if you have any questions, ask away.